Hello, this is Eric Hine with Microwave Journal. Welcome to this first EDI Con online educational day afternoon session on 5G, 6G, and IoT topics. Our platinum sponsors are Samtec and ComSol, and our track sponsors today are Mini Circuits, CPI Electron Device Business, Altair, Keysight Technologies, and Mori Microwave. We have a great lineup of talks, starting with our afternoon keynote session, Multiphysics Modeling of High-Speed Communication Devices, given by Andrew Strickwerda, Application Manager Electromagnetics at ComSol. Now I would like to introduce our presenter. Andrew Strickwerda is a lead application engineer at ComSol, specializing in electromagnetics. He received his PhD in physics from Boston University and conducted postgraduate research at the Technical University of Denmark. He was a senior staff scientist at the Johns Hopkins University Applied Physics Laboratory and taught at the JHU Whiting School of Engineering. Now I will turn the session over to Andrew.
Hello, everyone, and thank you for joining this session on multiphysics modeling of high-speed communication devices. In this session, we will explore the use of the finite element method, FEM, for multiphysics modeling in high-speed communication technologies, such as phased antenna arrays and 5G millimeter wave filters. The performance of microwave and millimeter wave antennas and circuits is pivotal for 5G, the Internet of Things, and satellite communications. By employing electromagnetic simulation software to assess these devices before physical fabrication and testing, the design process can be streamlined significantly, saving both time and effort throughout the development cycle. We will introduce an efficient modeling workflow for microwave and millimeter wave devices and demonstrate how to incorporate additional physical phenomena such as electromagnetic heating. The session will conclude with a bit of an overview on the advantages of multiphysics couplings that account for heating, mechanical deformations, and other physical effects. My name is Andrew Strickwerda, and I'm your speaker for today. I am an application manager for the electromagnetics team at ComSol's Burlington office, and you can read a bit more about me there. Before we begin, it's worth giving a brief overview of electromagnetics modeling. And this is because when we have multiphysics effects, it's important not only to correctly simulate the electromagnetic behavior of your device, but in many cases, you're actually coupling to other electromagnetic effects as well. This could be some type of voltage control on a dynamic device or some type of electromechanical actuation potentially. And so within ComSol Multiphysics, we have a number of modules from DC to daylight. On the low frequency side, we have the AC/DC module, inductive, resistive, and capacitive devices, things of that nature, motors and generators. Typically speaking, the RF module is the best suited for simulating high-speed communication devices. It's really tailored for RF and millimeter wave technologies, antennas, radar cross sections, transmission lines, and things of that nature, as well as those multiphysics couplings, such as microwave heating. At slightly shorter wavelengths, we also have the wave optics module, which is a bit more tailored for optical devices, plasmonics, scattering, nanoparticles, waveguides, photonic integrated circuits, and that sort of types of applications. And eventually we have the ray optics module, which is really more of an optical thermal structural analysis, stop analysis for pre-existing optical systems. And when we start doing analysis on these devices, it's important to consider what sort of capabilities you have and what sort of approximations and situations you need to consider. And so for a device like this handheld phone that you have on the right-hand side, there may be a number of different relevant wavelengths. On the sub-wavelength scale, you may have some type of capacitive screen where it's useful to simulate perhaps just an individual unit cell. It's likely that you want this device to be transparent to your RF frequencies, but still retain the capacitive touch screen-like behavior, and you can do that on these sub-wavelength scales. Sometimes it's also worth using more of a device scale, a small device scale to actually measure the composite behavior of something like, for example, this capacitive touchscreen. And also for the RF technology, you would want to simulate the underlying antenna and communications going on within this device. And so you may also be looking at the wavelength scale, for example, as in this patch antenna that we have demonstrated. And all of this can be done in ComSol Multiphysics in various fashions. You can have these individual small unit cells, you can have the larger composite geometry, and depending on your particular types of analysis, you can choose what portions of the device you would like to simulate, as well as what sorts of approximations you may want to make. For example, simulations in just a 1D geometry if you have some type of transmission line behavior, 2D geometries if you have translational symmetry, perhaps a 2D axisymmetric geometry if you happen to have rotational cylindrical symmetry, as well as full 3D simulations, which perhaps is the most common, as in many cases our CAD files don't necessarily have any particular symmetry that you can exploit. Regardless of the setup, however, we can do full solutions of Maxwell's equations, both in the frequency domain and the time domain, although there are a number of other considerations that may be worth factoring in depending on the particular type of analysis, such as if you're using a boundary element method or a finite element method. Do you have lots of open spaces? Do you have lots of inhomogeneous behavior? All of that can be accounted for in COMSOL multiphysics. As the scales get truly large, you also need to factor in exactly how you want to consider that. As I mentioned on the previous slide, you have the choice between the finite element method and the boundary element method. Generally speaking, the finite element method is a bit more general. It can be used very well when you have inhomogeneous material properties, and that's particularly relevant when you have heating in your model, as the temperature distribution will lead to gradients in your material properties. Finite element method can handle that extremely well. But as those model sizes get large, it can be very helpful from a computational perspective to increase the discretization order of your solution. That basically means solving at a higher and higher order polynomial that allows you to have a coarser and coarser mesh to simulate these larger structures in an efficient manner. On the other hand, we also have the boundary element method, and this will scale very well with size because you only need to mesh the surfaces of structures. For example, in this airplane simulation, RCS simulation that you see on the right-hand side, you can see that we are talking about more like hundreds of wavelengths of simulation here. And again, the computational efficiency is obtained there because with BEM, you only need to mesh surfaces instead of volumes. Of course, you can also combine these two approaches into what we call the hybrid FEMBEM modeling, where you have both the advantages of the finite element model as well as the advantages of the boundary element method. And on the left-hand side here, we actually see our first glimpse of what the COMSOL GUI is going to look like. This is just a portion of the GUI, but you see we have the model builder window here, and all of COMSOL is done in the same GUI. And so as you add in various physics phenomena, it's going to be all done in the same workflow, in the same interface. There's no need to export results and re-import results into another software tool. It's all the same interface, all the same workflow. All of the coupling is handled for you automatically. And in particular here, you see that we do have two interfaces, the electromagnetic waves frequency domain interface. That's what the FEM solution will come from, as well as the electromagnetic waves boundary elements interface. And under the multiphysics section, we have the electric field coupling that automatically handles the coupling between these two interfaces for you. Of course, ultimately, we're here because we want to look at multiphysics effects. Heating is the canonical case of that. Everyone is very interested in their particular device plus heat. As you put more power into your device, you may obtain better performance, but at some point, you need to factor in the thermal effects. Will the material properties start to change? As conductors heat up, the conductivity will decrease. What impact does that have on our simulations? Or, what is potentially more an everyday scenario? On the top-hand side of this screen here, we actually have a simulation of a spherical potato in a microwave oven. I think we all have experience with microwave dinners and that sort of thing. Again, we see an image of the model builder. Again, we have the electromagnetic waves frequency domain interface, except now we have added in the heat transfer in solids interface with a multiphysics coupling of electromagnetic heating. Again, it's going to be the same interface, the same workflow, all the same steps, regardless of the fact that we are now incorporating thermal effects in addition to the electromagnetic ones. And when we solve these thermal problems, this is typically done in the frequency domain for RF problems, but we need to consider the disparate timescales. RF simulations oftentimes are in the gigahertz, and so the time scales there are going to be on the order of nanoseconds. Thinking about this potato example, when you put something in the microwave, it's going to heat up over a period of 10 seconds or longer, a minute, and that is a much longer time scale than the RF time scale. And so what we do in these scenarios is we solve the electromagnetic problem in the frequency domain, and then we use time averaged heat sources that are then used in the heat transfer and solids interface, either in a stationary setting to get the steady state behavior or in a transient simulation. And I should note that these are fully two-way coupled problems between the thermal and the electromagnetics interface. And so if you are running your thermal problem in the time domain and the material properties start to change with temperature, COMSOL will automatically re-simulate the electromagnetic waves phenomena for you to get new time-averaged heat sources based on the thermal evolution of your objects. Here's a few other examples that you may see, and these are all examples from the COMSOL application library. We have the microwave oven example on the left. We saw that on the previous slide. We can also look at the specific absorption rate, or SAR, in a human head based on, say, a nearby cell phone. We can do things in the biomedical realm, skin cancer diagnosis, or simply RF heating. Maybe you have some type of waveguide, and of course you have conductivity losses in the metal itself. That can all be accounted for in COMSOL multiphysics. Once you have thermal effects, there's also a secondary multiphysics effect that you need to account for, and that's the structural deformation. Different objects have different coefficients of thermal expansion, and so as the temperature changes, we can see expansion, but also deformation and bending in our devices. It could be something as simple as a cavity filter experiencing thermal drift, as we see on the left-hand side. It could be the deformation of a PCB circuit board. The substrate and the metal traces will have different coefficients of thermal expansion, and as a result, they can potentially bend or warp. The third example we'll actually take a look at in the COMSOL model builder at the end of this session. That is a 5G cavity filter, and we'll see exactly what these thermal and structural effects have on the multiphysics behavior of the simulation. We also have another example on the right-hand side where we have a tunable piezoelectric cavity filter. That top hemisphere-looking object at the very top of this device is a piezoelectric diaphragm, and as the voltage changes, that moves up and down and changes the inductive coupling and therefore the resonant frequency in this cavity. We have a number of examples in the applications library in COMSOL that you can look at. Another one that we'll look briefly at today is the phased antenna array in the top left-hand side. When simulating these high-speed communication devices, it is, of course, very important to accurately model your wireless transfer. And so you need to be able to simulate your antennas and their gain profiles. We show how you can do that very efficiently in COMSOL with antenna arrays. You may also be looking at many of the other applications that you see here. I actually think the MRI coil is a particularly interesting one as well, when you start figuring in the effects of passive, medical devices inside of an MRI. Will it cause tissue necroscopy and that sort of thing? All right, at this point, we're going to turn to the previously mentioned example of an antenna array and take a look at what a fully developed COMSOL model of this will look like. And there's a few issues to discuss here. The first is that we're going to excite this structure with a lumped port. This is a very good approximation when your waveguide excitation is much, much smaller than a wavelength. We're going to account for the outgoing radiation using a scattering boundary condition that basically allows us to have a finite simulation space while still approximating radiation to outgoing to infinity. What we're also going to do in this model is actually demonstrate two different approaches. In one case, we're going to do a full simulation of this 8x4 array and show what that full fidelity model looks like. Of course, the downside of that approach is that more computational resources are required to do that simulation of the full device. And so we're also then going to show a secondary simulation where we only model one individual unit cell and instead use the antenna array factor to to generate the radiation profile of the full 32 element array from that one individual element. And of course, as a last step, we will demonstrate the agreement between these two approaches to show that the simplified model of an individual unit cell is a valid approximation. Here we have a few more results. You see the two models we'll look at the very top. We see we get very similar radiation profiles between the full simulation versus just one individual element. And we see a more quantitative comparison of their radiation profiles in the bottom right. And so now I've opened up a screen of COMSOL Multiphysics, and we see the exact plot we saw from the slide. In this particular simulation, we're actually applying two different phase shifts to the antenna array to demonstrate beam steering. And so here we see the agreement for an emission at normal angle of incidence. This is a 90-degree angle directly off from the antenna array. And as we change the phase profile, we actually can instead do this emission at a 60-degree angle. And we do see very good agreement between these two approaches. So let's take a quick look at how this is set up. Here we have the first component, and we do see the full 32-element array, as I mentioned earlier. We do the workflow in COMSOL is top-down, and so we'll build our geometry, assign our material properties. In this case, you see it's just a PCB substrate surrounded by air. Under this interface here, we have the physics assignments. We have a PEC ground plane, which we're just using for demonstration purposes, as well as assigning a PEC to the PACHA antenna itself. This lumped port group node is the 32 excitations to these individual elements. And as mentioned on the previous slides, we have the scattering boundary condition to handle the outgoing radiation and a far field domain node to calculate the far field radiated profile. We can see quickly what these simulation results look like. Now I'm loading up a quick plot of the electric field profile. Actually, let's look at this plot here instead, which this is actually demonstrating the electric field in the Z orientation on all of these patches. And you can see that we have this variation left to right with the phase parameter. If we change this to a different phase shift, we're now looking at uniform excitation, and we do see uniform profiles on these elements. We can also look at the beam steering with a 2D far field plot here. For the second component, this is where we are simulating just an individual unit cell. We again have the air and substrate as we did on before, but now we only have one individual lumped element because we only have one element that we're simulating. But as before, we have PEC for the patch as well as for the ground plane. On the left and right-hand sides, we're now using the periodic condition to approximate an individual element. We again have the scattering boundary condition and the far field domain calculation. If we go and look at the field profiles here, you can see again, we're solving for just one individual element. But what we then do is we create this array factor data set that allows us to generate what the far field emission would look like for the 32 element, the 4x8 array. And again, we can go and look at these comparisons here. We do see good agreement between them there, as well as here in a 2D cross section. Going back to our slides, we also can do arrays for triangular grids. It's very common in satellite applications, as well as in other fields, to have hexagonal arrays. And that can also be simulated in COMSOL Multiphysics. You can both simulate a hexagonal unit cell and then also apply the hexagonal array factor, similar to what we did in the previous demonstration. It does not necessarily have to be a Cartesian rectangular unit cell as well as a rectangular array factor. It is indeed implemented more generally than that in COMSOL. Turning our attention now again to the multiphysics effects, we're going to look at the thermostructural effects on a cavity filter. We again see the model builder on the left-hand side. We're again solving our electromagnetic waves frequency domain interface, but notice now that we have a solid mechanics interface and a heat transfer and solids interface with the thermal expansion multiphysics coupling. That's what will take the thermal effects calculated from heat transfer and apply them as structural stresses, thermal stresses in the solid mechanics interface. For this particular structure, we will indeed see a bidirectional coupling amongst these interfaces, and then we will solve the electromagnetic problem and show that the S parameters actually vary slightly. You can see that in the bottom right-hand side, depending on whether or not there is thermal deformation in our cavity filter. We do see a slight shift to lower frequencies as a result of these thermal effects. Opening the structure here, we can see there's a few isothermal contours, but let's actually go and take a look at the model itself. Similar to what we had before, we have material properties assignments. So you see that we have air inside the cavity filter. We have some dielectric for the interior of our coaxial connections. We have some coated surface. This is just inducing a little bit of conductivity on the inside surfaces. And notice that this is indeed a temperature dependent property. The bulk of the connector is aluminum. I should say this front surface here has been hidden. That's why we can actually see into the cavity. We have some adhesive layers as well as brass for our connectors. The electromagnetic setup is relatively straightforward. We have a coaxial feed on the bottom side. We have a coaxial outgoing port on the top, and we are accounting for the thin high conductivity on these interior layers using the impedance boundary condition. For the solid mechanics setup here, we are assuming that we have a rigid connector. Our cables themselves are not moving on the top and the bottom. And we're assuming a spring foundation. This allows a little bit of bend on these adhesive layers that attach the filter itself to the wall. For the thermal simulation, for demonstration purposes, we're assuming that the right-hand side is at a fixed temperature. These thin films have a small thermal resistivity as well. And we are also then approximating convection to the surrounding air, simply using a effective heat transfer coefficient of 5 watts per meter square Kelvin. And again, we have the thermal expansion, which takes the temperature distribution and generates the thermal stresses. We performed a number of simulations here. We actually did a straight electromagnetic simulation of the US and the EU bands in this frequency spectrum. We're around the KU is what we're looking at. And then we also did 2 thermal simulations as well, one of a uniform temperature distribution. This is just saying what happens if we have an isothermal change in the behavior. And you can see the types of temperature distributions we're looking at here. We then first solve the structural problem and the structural problem with that fixed temperature. And then on that distribution, we solve the electromagnetic problem. In this last case, we look at a slightly more general case where we actually simultaneously solve heat transfer in solids and the structural problem to get this non-uniform temperature distribution. And again, we perform the electromagnetic simulation on the subsequent device. We can see some results here. Actually scroll down here to the bottom where we actually do a quick comparison. You see the S parameters for the thermal deformation simulation as well as no deformation. And as mentioned in the slides, we do see that slight shift to lower frequencies. I hope you've enjoyed this brief presentation on multiphysics modeling for high-speed connectors and high-speed devices. We do have a number of additional resources on the COMSOL website. We have blog posts written by both COMSOL employees as well as guest bloggers, a number of videos that demonstrate workflows in certain application areas, user stories from customers of ours, as well as example models and various applications. Thank you very much for your attention, and I look forward to your questions.